Okay, thank you. So my name is Jeff Molyneux, and I'm the Executive Director at the Materials Joining Innovation Center. Contrary to what it says in the program, this has nothing to do with DC electronegative. This is all about looking at an alternate method for determining the hardness of hardenable steels. So one of the challenges that we have is answering the question of how do we get it right the first time? Welding hardenable steels, as anyone in the welding industry knows, is somewhat challenging. So when I say hardenable steels, I'm generally talking about medium alloy steels with carbon equivalents over 1, in the 6 to 1 and over range. Total carbon content on the steels that we'll look at today is, we've targeted around 0.4%. So these are hardenable steels. We do easily get a lot of martensite. But the question is, how do we get it right the first time? And of course, there's many tools that have been available for years to calculate these things and to estimate. When it comes down to it, welding, coupons, and testing them is the tried and true method of verifying what we're actually doing. So the question is, can we use thermal video to not only measure the cooling rate of a weld, but also to predict accurately the resultant hardness in the heat affected zone? So when I say thermal video, I'm talking about infrared technology and looking at the thermal cycle in a weld. So ultimately, the objective of this research is to predict the peak hardness in a heat affected zone. Ultimately, that's what we're after. Standards that are applied to a number of industries require maximum hardness values in the heat affected zone. We have to keep under those. But then on the opposite side, when dealing with quenched and tempered steels for different applications, for hard rock mining, for example, you need to ensure that you're not softening your heat affected zone too much, because the high hardness values of the base material need to be maintained in the heat affected zone and in the weld. So it's a fine balancing act, and you need to find that Goldilocks zone where it's not too hard and it's not too soft and it's just right. So what we've done is we've utilized a thermal camera to record, we're calling it thermal video, but the thermal history of a weld. Right now, we're just using a commercially available hardware. We haven't developed anything custom. We'll get into the details yet, but the method that we've chosen is fairly simple. First, we take a look at standard methods of determining hardenability of steels. The Jominy end quench ASTM A255 is a very standard test. It's a well-known test. So we're taking a look at the particular alloys and samples of the same material that we're reviewing and conducting the Jominy end quench. And while we're doing that, we're evaluating the thermal history of the Jominy sample from the oven to the apparatus, the test fixture, and looking at that thermal history along the way. And then we'll take a look at that and then measure the resultant hardness. Straightforward so far. So with that data, we're going to flip over to the welding side. and do the same thing, but look at the thermal history of the weld, of the heat affected zone in particular, and then attempt to, well, measure the hardness and then attempt to correlate the data. So can we accurately predict what the cooling rate is, or what the cooling rate will result in as a final peak hardness? So the equipment that we're using, like I said, it's off-the-shelf technology. It's not the $350 infrared attachment that you can get for your iPhone, and it's not a $120,000 laboratory camera. This is a standard industrial infrared camera. It's a FLIR T640, and we're using the FLIR software to go along with it. Ranges in this particular camera range from -40 to 2,000 degrees C. The material that we're using, of course, I never believe MTRs wholly, based on batch material sampling. I find never exactly what I want. So using optical emission spectrometer, we verified the actual chemical composition of 3 different alloys that we're looking at. 4340, 5140, and 1040 steel. So 2 very hardenable steels and 1 mild steel or low alloy steel with lots of carbon. So as you can see, the chemical compositions are all well within range. The carbon content is just hovering around that 0.4 mark. 4340 is what we'll focus on. We'll talk about a little bit about some of the other results, but based on the amount of time we have, not only here but also in the lab, we've focused primarily on the 4340. The nickel content here is one of the key things that helps the hardenability along with the, as an austenite stabilizer, it helps us to get the material nice and hard. So we're somewhere about here on the iron-carbon equilibrium diagram. For those of you that were here for the first presentation this morning, the heating rate plays a tremendous role in the reality of where these lines come in, as do the other alloying elements. So just a guideline. A little precursor on the Jomini end quench. The Jomini end quench is a test where you take a 1-inch diameter cylinder, heat it up, let it cool down. Heat it up again, and place it in a specific fixture that forces a constant flow of water against one end. And what that does, see if these videos work. What that does is it provides a very rapid cooling at one end of the sample and a very slow cooling, or a gradient of cooling rates throughout. This is a very long video. It's about 8 minutes long, so I've sped it up. What it gives you is the idea of where the resultant thermal gradient is. So a couple notes about some of these thermal videos. There's 2 ways to present the data. One is with a fixed peak temperature, which is what we see here. So as things cool down, you see the peak, the white, goes away, and in this case, we approach the nice yellow color, which is probably around 400 degrees Celsius. Okay? The other way, which you'll see in a moment, actually has the peak not fixed. So the maximum temperature in the video is the peak. So the hottest thing in the video always shows up as being that white or kind of white-red color temperature. So just we'll make note of that as we go along. So once this Jomini end quench sample is completed, the next step is to examine what the resultant hardness is. So the sample's prepared, and then step by step along the coupon, hardness is measured. This is not anything that is extraordinary. This is nothing new. But what we're doing is we're looking at correlating this hardness data with the thermal imaging video. So the result here, we had some spurious results with our 1040 steel, but the 5140 and the 4340, we showed very good results, correlating the distance from the quenched end to a cooling rate, a very consistent one. We have some good ideas as to why these deviations occurred on the 1045 steel, and so we're going to have to repeat some of that testing. But as we see here, very consistent results with the cooling rates to the end. 4340 steel is a very hardenable steel, so you get this nice flat hardness. As well, 5140, still hardenable, but a little less of a degree. Now, we look at some of the, again, very busy graphs. So, continuous cooling transformation diagram. Again, we need to take these things with a grain of salt. In this particular case, with a Jomini end quench, we've got lots of time for austenite to form. So we don't need to worry too much about some of the issues of not fully transforming to austenite that we see in weld metals in the heat affected zones. So we can see this, the colored lines, these are the actual measured cooling rates that we see at different distances from the end of the Jomini end quench sample. And we overlay it on the CCT diagram, and lo and behold, we find that things match. So this is a very good sign that we're able to predict, at least according to the CCT diagram, what the microstructure is going to be. So we had the first few, I guess it's the first 6 indentations on the sample were fully transformed to martensite, and the remainder were changed to bainite and martensite mix, depending on where in the bainite nose they fell. Sectioning the sample, looking at the microstructure, again, confirms everything that we expect from such a sample. We see acicular martensite, very hard and brittle in the closest samples to the end. We see some lath bainite along with martensite in the latter portions, and then just some martensite and bainite mix closer to 50-50 there out at some of the cooler, slower cooling rates. So far, we're very, very happy with these results. Exactly what we would have expected. Measured cooling rates with the 5140, again, same thing, different CCT diagram. Things are pushed a little bit out to the left, so we are able to still maintain a martensitic and bayonetic structure along the way. Just a little note about the heat-affected zone thermal cycle. I think this particular figure has been thrown up on the screen several times in the last day and a half. So most of you would be very familiar with the thermal cycle in the heat-affected zone. But what we're looking at is this grain coursed heat-affected zone primarily. where we end up getting up over the austenizing temperature and then cooling down very rapidly. Again, we're looking at predicting the hardness in the heat affected zone. So this is a bit of our setup. We have a torch running a Fronius power source with a solid wire, 8515 gas, pretty standard parameters here. Running it on a buggo just for consistency's sake and to make sure that we don't get hands and gloves in the way. And up here we have positioned the thermal camera. Now, one other thing that we did is we built a shield around the arc. This protects the camera, but it also prevents us from ending up overloading the sensor and making sure that we don't end up with a whole lot of extraneous data and interference along the way. So this particular sample that we're looking at was 4340, half-inch thick, and it was cooled in air. It is sitting on a steel table, so there's a big thermal sink there, and it was not preheated. Okay, that comes into play a little bit later. So we're looking at measuring the thermal cycle. Okay, so we're not looking at making a good weld here, and you'll see that in a minute, what happens when you weld 4340 without preheat. So, but this is the video. So you can see here the top end of the scale is moving, and lo and behold, it's really hot in the middle, and it's not so hot on the sides. I mean, this would be pretty well what you would expect. But the area that we're really paying attention to is right in here. So this is the thermal cycle. The measurement points that we're looking at, we've got 14 data points right at the fusion line. 3 of them are in the weld metal, and the remainder are in the base metal. A little close up, you can see we've identified these points, and the yellow line there is our fusion line. And what we have here, a little bit of detail of to how far these points are. They're very close together. We are limited by the resolution of the camera, the frame rate of the camera, but nevertheless, this was what we found. The maximum temperature formed was around, in the base metal, was around 860. So, this is another picture of the same weld. This time the peak temperature is fixed. These are just some interesting data points that we look at just to give you an idea of what it looks like as the data is being presented. Follows along. You've got some reflections off of the shield that we used. Things cool down, oddly enough. So then we look at the weld microstructure. So 6 areas of interest up at the surface here, and there's a good reason for this on the surface temperature, because that's really what we were looking at with the thermal camera. We're not able to see what's going on subsurface. So the thermal camera is a visual thing. It's looking at the temperature of what you can see. So contrary to popular belief, thermal cameras don't see through walls unless those walls are made out of thermally opaque or thermally transparent material. So not all the movies are right. And then we've got these areas down here in the heat affected zone subsurface. So taking a look at, not only can we correlate the hardness data on the surface where we're actually looking, can we interpolate that data and look and figure out what the peak hardness is going to be subsurface. Microstructures are notoriously difficult to see on PowerPoint, but we'll try to describe it. We found hard stuff. Okay, lots of martensite. We pretty much expected that. Okay, we found what we were expecting, and here's where the real results are. So our surface hardness predictions, we came up with some, based on all this information straight out of the thermal camera, we came up with some predictions in the low 50s, right around 51. Okay, in these areas here, these measurements, there's 6th through the 10th data points, we didn't make any predictions, primarily because we didn't get into the transformation zone. We didn't get hot enough to fully transform into austenite. So based on the rapid heating cycle and the rapid cooling, we were not expecting any martensite in these areas. Okay? So back to our prediction, we were pretty close. So the actual hardness in these areas was very close. So we're pretty happy with the initial results here. Less than 4% error on one, less than 1% error on the second point. The initial point here, right on the fusion line, we weren't able to measure that accurately because of the interference with the weld. So next steps, we're going to end up just machining that weld cap off nice and flat and going from there. But we'll talk about next steps shortly. So this is what the surface hardness distribution looked like. So this is a top view of the weld. Maybe not obviously, but that's the weld bead. And these are all the hardness indentations from the fusion line out. And as you can see, not surprising, really close to the weld, it's hard. And as we move away from the weld, the hardness returns closer to the original base metal hardness. Unfortunately, using Rockwell C, we're really not getting a highly dense measurement of these hardness points. So again, that's an area for improvement going forward. Cross-sectional hardness distribution, again, very good correlation. Not quite as good. We see spikes upwards of in the mid 50s, so closer to an 8% deviation from what our predicted hardness was. So we've got some work to do there, and that's the hardness again. You know, the Vickers hardness map is going to be much more telling when we look at that in relation to these cross-sectional hardness distributions. And then I don't think you can see it, but from about here to here, we have a beautiful underbead crack that nearly popped that weld metal right out of the plate. So it is not recommended to weld 4340 without preheat, just for those of you that don't know that. So some of our limitations, as I mentioned, we do have some limitations with this process. The camera resolution is one of the primary ones. So it is a fairly high resolution camera, but high resolution for a thermal camera isn't the same as your high resolution on your phone. We're a 640 by 480 resolution, so you got to get pretty close. The camera frame rate, we're able to record video at 30 frames per second. When you're dealing with cooling rates that are very fast, that has some limitations. We can't exactly capture every fine detail in the milliseconds after the weld passes. course, we were using the commercial software that was provided by the camera manufacturer. And this software in itself has some limitations. So looking at that going forward, there's certainly opportunity for improvement there. Currently, all of the predictions that we're making are based on actual geometry data that we've done. So in order to look at a particular alloy and predict the hardness on a weld on that alloy, we would need to first have a geometry end quench. There is some opportunity to expand it out from there using the calculation method in the ASTM A255. We have yet to correlate that with the data. So, in conclusion, we were able to use the thermal video to predict fairly accurately the surface hardness of the weld heat affected zone. Limitations do exist. My hope would be that in a coming day there would be a fairly easy to use tool that a supervisor could kind of lean over the shoulder of a welder, take a video, take a measurement of what that welder's doing, and accurately predict the hardness in the heat affected zone of that exact weld without interrupting the welder. Future work, obviously we have further testing to go, different carbon contents, looking at hardness relative to Vickers, the micro hardness, Vickers macro, but at a much more dense measurement point so that we can ensure that we're not missing any big hard spots. And then looking at the experimental study to verify the effect of preheating. We know that preheating slows down the cooling cycle, but how does that play a role when you're looking at it with a thermal camera? And then ultimately it's the real-time prediction based on the thermal video. Any questions?
Questions?
Patricio.
This is awesome, Jeff. Super awesome. I think you have gold in that data you have here. I have a question. When you show the cooling rates, you got halfway here.
That one?
So in the yellow curve in the cooling rate, you see it kind of has like a shelf there,
Yes.
right? So that shelf in this case is the martensite transforming, right? So you could have a sense of at what temperature you're having the transformation, and I think that could be a useful information for assessing quality of the weld. For example, if you have not martensite but something else, bainite, would be a higher temperature. You should never have martensite anyway, right? But I think there's so much there to squeeze.
It is a very powerful tool.
I hope it gets used in practice. It's easy for me to get excited. I hope the inspectors get excited.
So we simply took the cooling rate of the geometry sample and the resultant hardness from that sample and said 100 degrees Celsius cooling rate resulted in a 50 Rockwell. Throwing numbers out there. So then taking that correlation from the geometry and relating that to the heat affected zone. Absolutely. Correct. So, these ones here are a full diameter apart. There may be some interference. We're looking forward to getting more dense readings with microvickers. So that's the next improvement. Adrian?
So in terms of the validation of the temperatures, the emissivity can sometimes get skewed a little bit. Have you tried doing any kind of correlation with small welded thermocouples to see how well they track with?
Not yet. The emissivity issue comes into play with, right now, we're assuming that it's working itself out with the Jomini end quench. Because we're looking at an actual measurement on the Jomini, and we're correlating that, so we're hoping that it doesn't matter.
Yeah, I think my concern would actually be, I think the weld is fairly well shielded, so the oxides that kind of build up or whatever, or if there's maybe soot, that would be maybe a concern that it starts to build up, something like that. But the Jomini, I think I'd be a little bit more concerned about, because it's kind of spending like 8 minutes cooling
Yeah.
in open air. So I'd be kind of hesitant about how accurate the Jomini temperatures might be. So it might be worthwhile just to instrument the Jomini actually rather than the weld.
So the numbers that we're getting on the cooling rates from the Jomini very closely match the cooling rates that are published in A255.
Okay.
So they're very close.
Oh, okay, that's
Yeah.
Yeah, I have the same comment. If you could explain the difference between the low carbon steel, which you said didn't match.
There were some experimental issues with the low carbon steel. The sample was a little bit subsize, which potentially could have caused that, but there are other avenues. I don't think it's good data, the 1045. I just didn't have a graph that didn't have it on it, so I couldn't pull it out.
Any other questions? Anyone else?